All right, we will go ahead and get started. Hi, this is Graham Stevens from KETIV. I am here presenting a presentation on HFSS and circuit synergy using circuit instead of RLC boundaries to speed up your HFSS simulations. For this morning, we'll be going over this method of using circuit substitution for RLC boundaries for passive components, discussing when it applies in terms of what simulations, and then doing a demo of how to set this up, the workflow and results, and finally Q&A at the end. And I should preface this as well, this is really focused mostly on HFSS in this particular RLC boundary in terms of simulations. So just to introduce myself, I'm an application engineer here at KETIV, focused on Ansys products. I have 25 years of experience in product development, consulting, and simulation, and I'm providing application support for Ansys high and low frequency electronic applications. So in HFSS, there are various boundary conditions. You can sort of see this from the help, perfect E, impedance, radiation, and so forth. And one of them is lumped RLC boundaries. And this is our focus today, is on this type of boundary condition. And this type of boundary condition of lumped RLC is one way out of many to examine surface losses and model surface losses. So within HFSS, we have a finite conductivity boundary, an impedance boundary, layered impedance, and finally lumped RLC boundaries can model losses in the system. And a lumped RLC boundary is an area, so we select a certain sheet area, and in that area we essentially create a lumped resistor, inductor, or capacitor in parallel on a surface and create that lumped RLC boundary. And this circuit here is showing an RLC in parallel. And then similar to impedance boundaries, this following condition holds at lumped RLC boundaries where we have the E normal squared divided by the impedance times 0.5. And unlike impedance boundaries, you're not required to supply the impedance per square, but you must supply the actual values for RLC. And then HFSS determines the impedance per square of the lumped RLC boundary at any frequency. And I should also say as well that this came from the HFSS help discussing lumped RLCs in parallel on a surface. You can also do it in series. So there's an option here as well for series. This is essentially sort of an approximation, and it's useful in a number of situations. So if I have a strip line and I've got a component that you can sort of see, maybe a chip resistor or an inductor in line with the strip line and a surface mounted component, we can essentially approximate this. Instead of modeling all the geometry here for the surface mount component, you can use just a sheet and this RLC boundary to model this situation. Some other applicable situations where this method is useful is if I have an inductor and I'm doing a matching capacitor relative to resonance. Might be impedance matching an antenna, a resistor and a Wilkinson power divider, frequency selective surfaces. There's a number of different situations where you might have a passive that you're interested in approximating or playing around with in your HFSS model. So today then I wanted to just introduce this method of speeding up your simulations. So the typical RLC boundary simulation is depicted at the top here, where you use HFSS only. And so I have my simulation. I put my passive into the simulation with the RLC boundary, and then I simulate and I get a value. And if I am interested in changing or optimizing what those RLC values are, the resistor, the inductance, or the capacitance. I have to simulate, I have to change those values in terms of an optimization or parameterization. I change those values and I rerun the HFSS simulation and I get the results. And you have to rerun an HFS simulation each time you're changing those values. And where this method of using a circuit substitution instead helps is if I'm doing a lot of optimizations or parameterizations of those values, I can, if I shift that, if I shift those optimizations into circuit, I can go much, much faster. And so the method here is to change out within HFSS, change out the RLC boundary for a port and use a port instead. And then take the resulting model results and feed the port S parameter data to an equivalent circuit, which I'll discuss or just to demonstrate in a few minutes, using an import or the dynamic link feature of HFSS, and then do a linear analysis in circuit where the R, L, and C values are within the circuit and changeable within circuit. And so the HFSS data essentially stays constant. And then as I change the RLC values within circuit, I can get equivalent results to the HFSS only simulations. And the circuit tool runs very fast. And so that speeds up your simulations dramatically. So as I was just saying, with a little more setup overhead where you have to create the circuit and validate your results between the two, the circuit run when I'm changing R and L and C values is much, much faster than rerunning an HFSS run. And so this makes explorations and optimizations of the RLC values computationally tractable in some cases, but also just speeds things up dramatically. So there are a few limitations. You never get anything for free. RLC boundaries and ports are approximations, and they're formulated slightly differently. For example, the port assumes the E field to be parallel to the length of the trace, while RLC boundaries do not have this limitation. And at higher frequencies, sometimes artificial resonances can occur. And so the equivalence of the RLC boundary and the port may not be exact at higher frequencies because of these artificial resonances. And so to avoid that, you may need to increase the level of detail in your analysis. Use the actual RLC component geometry, make sure the traces are equivalent as opposed to sheets, etc. But within this restriction, it's still much, much faster analysis. So now I'd like to switch to the demonstration phase. And I'd like to demonstrate how this is done. So for the model that I'd like to discuss right now is a simple strip line model here. So I have an air box here. I have some polyphon guide here and a vacuum for the whole region. And then I've modeled this as a strip line with just some finite conductivity sheets. So we have a ground at the bottom. We have a trace here, another trace there. And in between the two traces, I have a very thin, small lumped RLC area right in between the two sheets. For this model, let me just hide the air box and hide the vacuum. I have wave ports here of a fairly large wave port and a wave port in and a wave port out. And we'll be looking at the insertion loss and return loss of this system. And so for this microstrip, I have created these sheets in terms of the geometry. And then for the boundaries, we have a standard finite conductivity ground and trace 1 and trace 2. And then here I've done a lumped RLC port here where I'm in this case using parallel inductance and capacitance. And I've just named these as variables L and cap. Oh, sorry, excuse me, it's update data, give me a second. And I'm using a capacitor of 3.79 picofarads and an inductor of 10 nanohenries. And so then for my excitations, I have a wave port here where I'm just doing a 50 ohm standard wave port and a second one here. And then I have done some mesh operations on the traces, and then also another mesh operation on the lumped RLC. And for the setup, we're looking at roughly 8 gigahertz run, standard auto select directed iterative, saving fields. And for a sweep, we're just doing 0 to 8 gigahertz to get results. And then when we look at the results, we have our, I've run a couple of different analyses where I'm changing the RLC values, and you can see that we have 4 different analyses here for my nominal 3.7910, which is in green. And then I changed the parameters a few times to look at my insertion loss S21, and similarly return loss here, and different values to play around with return loss. So this is a sort of a typical strip line model that you might be interested in changing these values. And when I was doing these analyses and running the optometrics here, it was taking, here we can just continue running this briefly, just to get a sense of the time here. So for this relatively simple model, it's now setting up and doing an adaptive pass. While the model itself is, fairly quick, we only have 3,500 tets for each of these passes. It takes a while to do a pass. We can see where it's taking us at least, a minute or two to run this particular next scenario for optimization. Let's just take another minute. So it finally completed the adaptive passes for this single run and is now doing the frequencies. All right, so then we have our value here where we just ran another run here and can plot that. So a different setup for the equivalent run or the equivalent model is to then create the same strip line model where I have all the same geometry in terms of the lump port is still here, but I've taken it out and it's no longer in the boundary. So it's not really in the model per se. Instead, I've replaced it with a lumped port here. Again, a 50 ohm lumped port. The integration line is the same as the RLC. The RLC has a current flow line as well, and simply replaced that RLC boundary with this lumped port, ran the analysis. You'll notice there are no results here. So the results for this model are now because you have a port here instead of RLC values, you can't get it, these results. If I plotted them, wouldn't mean anything. To actually get results that are equivalent, we need to now go to a circuit model and create a circuit model. And so when I create the circuit model for the equivalent, I have my port 1 coming in, I have port 2 coming out, and then I have the lumped port has a port here where I create my parallel inductor and capacitor to ground as an equivalent circuit, essentially. And now within circuit, I can modify this L and capacitor value very quickly and run an analysis within circuit and get equivalent results. So if so I'm creating within circuit, I have created these port 1 and port 2, and they are standard 50 ohm, 50 ohm impedance ports. I've created a power sinusoidal with my 1 watt excitation, just like I did for the stripline model here, where we have excitations of 1 watt into port 1. And within circuit, then I took the stripline model, no RLC, and basically dropped it onto the circuit. And that creates this HFSS dynamic link. So you can create an HFSS dynamic link like I just did. You can also create a, if we go to the stripline and results here and go to simulation data and display all frequencies for the matrix data and export this data and save it, not overwriting the solution renormalization or including these constants or comments. We can export that S parameter data, and then within circuit, go to the component libraries and grab yourself an import and grab that particular data that is S parameter data that we just saved and drop it into the circuit. And this import object will be equivalent to the dynamic link. Obviously, the dynamic link is a little bit easier because I don't have to save results and then update the import model. Rather than going through all of that, I can simply right-click on the import model and just refresh dynamic link if I change the HFSS model in any way. And so the dynamic link is certainly a little easier to work with. And then for the results, we'll see that our S21 results here. Let's see here. Just analyze, run this. So you can see how that was the equivalent circuit run. It took, a second or two. And so if I change RLC values, again, it'll be a second or two for each one of those, and I can run through an analysis of different RLC values much, much faster. And it's hard to see, but this is the S221 curve. They're basically right on top of each other at this relatively low frequency. If I go to the return loss equivalent plots, they're a little bit different. So you'll notice that we have the return loss for the RLC with the RLC model is here, and return loss with the circuit-based model is here, and they diverge a fair bit at this higher frequency. And the reason for that is what I was saying before in terms of the when I look at the port versus when I change this RLC boundary to a port, they are slightly different and they do resonate differently at higher frequencies. And so you may have to go to get a less of an approximation that we're using right now. So we're using surface boundaries. I'm using for strict line, I'm using just a finite conductivity boundary. It's just a two-dimensional object. Maybe I need to go to 3 dimensions and actually get a sheet of copper there instead of my approximation. But you can you get these equivalent results at lower frequencies, depending on what you're playing with and looking for in terms of trying to optimize your RLCs, and or they may be slightly different, and you have to again sort of play with what level of accuracy do I need to get these closer. I can pull these a little closer if I increase my accuracy. I can pull these a little closer if I model a different level of detail. So in this particular case, I'm just interested in this S21, and these are almost identical. And so therefore, I'm feeling pretty good about the circuit model giving me the types of results that I'm looking for. And sort of equivalently to what we were looking at before, when I run this, the equivalent setup optimization or optometrics analysis, I can now run different RLCs, and you can see each second which just ran 21, 21, 31, 32 combinations. And now when I look at the update the plot, I'm looking at this one here. So now we can see for S21, those 32 variations are all plotted here, and I can, find and search for the right RLC values that I'm looking for in a much faster way of doing things. So that is what I wanted to show you guys in terms of sort of tips and tricks and ways to use the circuit tool. And then just wanted to sort of open up the floor for questions. Which you can put in the chat. Okay, so there was one question here from Mike. How wide does the RLC boundary need to be if you're changing physical items in HFSS within the optometrics run, such as the trace width in this example? How does one select which width the circuit uses? So the width of the RLC boundary, it sort of depends on your geometry. So if we remember this is sort of an approximation, let me try and, so we could have this RLC boundary be pretty wide, and we would get a slightly different, there's the RLC boundary here, and we would get a different result in terms of how equivalent these two are at different, high frequency versus low frequency with this wider RLC boundary. And so the sort of the differences between the RLC boundary and the port when they're wide versus when they're really thin might be very different. And one method of trying to get those two to be closer is to actually shrink this width of this boundary to much smaller. So in my previous example, I had it as a really thin area versus this thick area. That's obviously different from a if I know my resistance values on the basis of sheet resistance, then I'm still playing with. I'm still changing from reality in terms of when I actually put an RLC, when I actually put a resistor here or an inductor here, it's going to take up a certain amount of space and have a certain area. And so the answer is, I think, Mike, in terms of this is sort of play with it in terms of potentially going to much smaller widths here, or gaps as well, depending on your circuit, to see if you can get better equivalence between the RLC and the port. Does that make sense? But in terms of the width here as well, when I have a really thinner, a much thinner region, you can, it really helps within HFSS to then create, here I'll show you, to create these mesh assignments here where I increase the amount of mesh within this small area to just increase to get to converge to your solution much faster. You would, with much smaller, less wide traces, you definitely want to increase the mesh in that area so that you converge faster and better. Whereas if I have a wider one, I may not have to worry about that quite as much. Any other questions? So somebody says, I'm confused by the fact that your HFSS linked element in circuit is 3 ports. In my mind, to recreate this situation, there should be 2 HFS links with the LC components linking the 2. By putting those values to ground, you're assuming symmetry in the model. Is that safe to do? Let me try and 2 HFS. Confused by the fact that okay, confused by 3 ports. So the 3 ports here are corresponding to my substitution of a lumped port within HFSS here, where I have the lumped port here. And you're saying we should be 2 HFSS links with the LC components linking the 2. So I'm not sure how you're, should be 2. I guess, Anthony, if we could talk offline relative to what you're proposing in terms of 2 HFSS links with the LC components linking the 2. We can talk more about this in terms of ground. Yeah. Kind of within, this sort of brings up a whole nother topic. Within the circuit model, if we edit link definition here, whoops, wait a minute. Sorry, edit the symbol definition and the pin properties, you get to this pin location editor here, where right now I'm using an applied reference to ground, and you can also add individual reference pins per port. So this sort of kind of opens up a much wider topic relative to ground within HFSS versus circuit. So circuit definitely has this implied reference to ground, whereas HFSS doesn't. And there's just, yeah, this is a much larger topic. Anthony, I will let's connect a little bit later in terms of trying to answer your question more directly, and I'll try and post something else in the chat or something in terms of to the wider audience, or in terms of comments to the YouTube video as well. So any other questions? All right, well, with that, I just wanted to conclude here relative to if you're doing optimization of RLC values in HFSS, you can dramatically speed things up. If you use the circuit tool in combination with HFSS to model the changing RLC values. I should say as well that for the setup for the circuit, we inserted this analysis here for a linear frequency analysis and did the same 0 to 8 gigahertz range that we did in HFSS to enable us to get our S parameters and sort of an equivalent circuit. So maybe that's part of the confusion as well, I think. With that, I just wanted to annotate some additional resources. So if you do not have access to the Ansys Learning Hub, it's a repository of a lot of webinars and useful information in terms of help for HFSS. There are a couple of relevant courses relative to what we've discussed here. Within HFSS Getting Started, there's a boundary condition section. There's an AEDT RF passive circuits course. And finally, another course on co-simulation using HFSS and circuit within AEDT that are all applicable. We'll go over a few more examples and demonstrate things a little further. And then as usual, if you do have any questions or need any help getting set up on this, it's not working as you're expecting, or running into issues, please do contact support@ketiv.com, either through email here, support@ketiv.com, or by phone. And then KETIV itself offers simulation services within the Ansys portfolio, mechanical, fluids, and electronics. So if you have analyses you're looking for to form out, KETIV can do these types of simulations for you. We also obviously are trying to enable customers to do it 100% themselves, and we do anything in between in terms of mixing and matching and getting you going. So please do keep us in mind if you have overflow jobs or other analyses you're looking for help with. And finally, one last thing here is we have an upcoming event. Next week's KETIV Virtual Academy is covering what's new in Autodesk Inventor 2023. And if that's of interest, please do register at ketiv.com//learn. And with that, I think we're all finished. Thank you so much for your time and help. And we will hopefully see you again in a month or two. Take care.